All right, I want to do a short video introducing a couple of concepts which are going to make the problem solving session more interesting. We can have a more diverse range of problems for this week. And those are basically the relativistic Doppler shift and some ideas related to Lorentz transformation of solid angles and things like that. Now, in the previous video, I basically computed what would be the power radiated by an accelerated charge in a relativistically correct formalism. And I just want to make one qualifying point about the derivation, which is I said that the power radiated is Lorentz invariant. And I just want to qualify this by saying that this is only true as long as there is kind of a front back symmetry in the way the particle emits. So this is only true if the momentum in some direction of the emitted radiation is going to cancel the momentum in the exactly diametrically opposite direction. And let me say why that is the case. So the numerator here is basically energy, right? So this is the energy of the photons which are being emitted. And that's going to transform as the zeroth component of a 4 vector. And the 4 vector in this case is the 4 momentum, right? Now, if you're talking of the radiation with that symmetry, then the 4 momentum is going to have the zeroth component, which is just energy divided by c. And the other 3 components will be 0, right? Because the net momentum is going to be 0 on any of the axes. So then energy is going to just transform as E equal to gamma times E dot, right? You're never, the other terms are going to be 0 because the first component of the 4 vector is 0. There's only the 0th component in this case, which is not 0. Now that's not true if you don't have that symmetry, because if you don't have that symmetry, then the 4 momentum for the radiation, the 0th element will be E by C. And the other 3 elements are not going to be non-zero necessarily, not going to be 0 necessarily. So then you'll have to write the whole thing out. So I just want to qualify this by saying that this becomes Lorentz invariant only if you have that symmetry in the radiation, such that the net momentum radiated is 0. If that is not 0, then you know this is not going to be Lorentz invariant. So don't take this as a kind of a given axiom that power is always Lorentz invariant. That's not true. It actually depends on the angular pattern of radiation, whether power is Lorentz invariant. Okay, with that out of the way, I want to talk about relativistic Doppler shift. And I want to do that, kind of kill 2 birds with 1 stone here. I want to do this by also introducing a new 4 vector. And that comes from the realization that phase has to be a Lorentz scalar. So I'm going to give you kind of a heuristic reason for it. Let's see if you find it convincing. So anything which you can measure, some measurable quantity has to be a Lorentz scalar, right? So number of photons is always conserved in all frames. Number of electrons are conserved. Number of anything has to be conserved. Otherwise, we can't have the same physical laws if we can't agree, if inertial observers cannot agree on, you know, number of countable things. Now, phase is basically a measure of how many crests or troughs have passed by, right? So you're really counting things here. How many crests are there? How many troughs are there? And that's kind of the heuristic reason why phase is a Lorentz scalar. I myself find that semi-convincing, but let's say for now, assume that phase is a Lorentz scalar, which means that you can write it as an inner product between 2 4 vectors, right? Now, the first 4 vector is kind of obvious because phase itself, you know, the equation for phase is k dot x minus omega t. So you know that x is involved and time is involved. So it kind of makes sense to write the first 4 vector as ct, the 4 position basically. And now the question becomes, what should be here? What should be the 4 vector here such that you get a Lorentz scalar? And if you want this equation to come out, then, you know, you can pause the video and check it. It's pretty obvious that you need to have omega by c and k vector. And so that must be a 4 vector, right? So we call that a 4 wave vector because k is the wave number. So you just call this the 4 wave vector. And now that you know it's a 4 wave vector, you basically immediately have the Lorentz transformation. So if I want to Lorentz transform the 0th element, then I get omega by c equal to gamma times the 0th element in the k prime frame. That's omega prime by c plus beta times the first element in the k prime frame, which is kx prime. Okay. Now let's say the wave vector makes an angle theta prime with x prime, then you can write kx prime as, I'm basically casting kx prime with an angle, right? So kx prime will become, the total magnitude of k, which is k prime times cos theta prime. Now, if you're in vacuum, then you have c times k prime equal to omega prime. That's the dispersion relationship in vacuum. I mean, what I'm doing here is I'm trying to get rid of k prime. So I have an equation only in terms of the omegas, right? Yeah, so you use the dispersion relationship in vacuum and you get rid of this. And then you get the equation for the Doppler shift. Okay, so you get omega is omega prime times gamma times 1 plus beta times cos theta prime. If you want to have all of this in, if you want to have the angles in the observer's frame, that is k frame instead of k prime frame. I mean, I keep saying observer because we're going to always call the unprimed frame as the prime where the observer is. It's kind of thinking of it in just in a personal sense, think of it as the lab frame or the frame where you are and you're observing something. And the prime frame is usually always going to be the frame in which the particle is at rest, which is emitting, right? I mean, that's the common terminology we are going to use. But anyhow, in this case, it doesn't matter what the k and k prime frames are, other than the fact that beta is the velocity of the k prime frame with respect to the k frame. Anyway, you want to cast all of this in terms of the unprimed quantities, then you can use the equation for the aberration of light to basically see the transformation of angles, right? We did that already. And it's a nice thing to remember that gamma times 1 plus beta cos theta prime ends up being 1 over gamma times 1 minus beta cos theta prime. So you just flip the index on gamma, gamma becomes 1 over gamma, and then you flip the index on beta, flip the sign on beta, and then change prime to unprimed. You can go back to the equation we had relating angles between two frames, and then you can show that this is the case. Anyhow, so this factor is called the Doppler factor, the relativistic Doppler factor. And there's something curious going on here in this expression, which is, let's say you didn't know special relativity and I asked you to derive an equation for Doppler shift, you would have derived exactly this without the gamma, right? So that 1 minus beta cos theta is the component of the velocity along the line of sight connecting the emitter and the observer, right? So this would have just given you the standard Doppler shift without the gamma. Now there's an extra gamma here, and that purely comes from time dilation. Okay, so there is no non-relativistic analog to having this gamma. It's a purely relativistic effect, and it comes just from time dilation. So it just comes from the fact that the clocks are running at different rates, at different speeds in the two frames. Okay, so it's important to remember the distinction because what Doppler factor you use will depend on what you're actually talking about. So that 1 minus beta cos theta is that simple effect which you know from high school, really, where the example given to you was a train which is approaching you, and then it's blowing its horn, and then you see that its pitch is higher, and then the train passes by you and the pitch is lower. All of that, all of the wave crest adding up, the wave getting compressed, all of that is in this 1 minus beta cos theta. Now this gamma here is a completely relativistic effect. It is just coming from the fact that the time itself is running at a different rate in the two frames. Okay, so with the same, you can kind of make a distinction between the transformation you'll use for time. So if you remember, we did time dilation and we said that delta t is delta t prime times gamma, right? That just tells you the dilation in the rate at which the clocks are running. Now, suppose I ask you a question where you're standing at a place and then your friend is going to send you laser pulses every second, but your friend is moving away from you, or moving with respect to you. What is the interval of time between the laser pulses you are going to see then you have a conundrum. Then you can't just use you can't just say that the duration between pulses is just gamma times delta t prime, right? Because that gamma accounts for the fact that your friend's clock, which he or she is looking at to time the laser pulses, and the clock you're looking at to measure the received times of the laser pulses, that gamma accounts for the fact that those two clocks are not going to agree with each other when they take. But also your friend is moving, so you have that classical Doppler shift, right? So your friend might be coming towards you, in which case he or she is catching up with the pulses which are being emitted. So there's that foreshortening because of the classical Doppler effect. So if you want to measure, the total, if you want to actually predict what will be the time interval between your receiving of the pulses, then it's going to have to be both those effects combined, right? So in that case, you would say delta t is delta t prime times the relativistic Doppler factor, which has a gamma for time dilation, but it also has this factor, which is, the canonical Doppler effect. Okay, so just it's good to get your intuition around this to know which delta t you're going to use when you do a lot of calculations, right? It all comes down to what you're really talking about. Are you just talking about the rate at which clocks run, or are you talking about the rate at which you in the lab frame are going to receive something, right? So if it's the latter, then you have to use the correct Doppler factor, because you have to actually account for the Doppler effect other than the relativistic time dilation. Okay, now the same applies for frequency as well, right? This is the canonical Doppler effect for the frequency, and that gamma is a purely relativistic effect that comes from time dilation. Now, I don't think we'll be using this in the course, but just know that what we have done here for the four vector is valid in vacuum. But if you're in a medium, then this is the correct way to write the 4-wave vector, okay? So you're going to have k dot u, where u is the velocity of the plane wave in the medium. So if that is not c, then just be aware that you have to use the right form. Otherwise, you end up getting strange results that don't make any sense. Anyhow, so the last thing I want to talk about is angular distribution of power, and then we'll also talk about using the dipole radiation pattern and then seeing how that transforms between frames. Again, this is just some exercise in some geometric ideas which we have already had. We derived the aberration formula, right? So we had cos theta is cos theta prime plus beta divided by 1 plus beta cos theta prime. Now I just want to set up the transformation of solid angle, because I'm going to use it later. And the idea is, how does solid angle transform, right? And that's pretty straightforward. Just a little bit of differential geometry. So d omega prime, so solid angle in the k prime frame, is sine theta prime d theta prime. Sorry, these have to have primes here, d phi prime d theta prime. Actually, d phi, whether you prime it or not, doesn't matter. Why? Because phi is measured in a plane perpendicular to the, I'm measuring phi in a plane which is perpendicular to the relative velocity, right? So there's no change in the lengths or angles measured purely in a plane perpendicular to the relative velocity. So you're going to have a situation where d phi prime and d phi are the same. So whether you prime it or not doesn't matter. And of course, theta is the angle made with the x-axis, right? So I've just defined here that the relative velocity is along the x-axis. So theta is just the angle made with the x-axis, and let's say that's the polar angle, and then phi is kind of the azimuth angle, right? So the angle phi lies in the yz plane, right? So it's not going to be affected by any aberration. Now I'm going to write sine theta as d of cos theta, just to simplify the algebra, because I have an equation for how cos theta transforms. And yeah, so I'm going to now try to cast this in the unprimed frame. So this basically becomes, again, this has to be a prime, I'm sorry, d of cos theta prime. Yeah, so you just do the same for the unprimed frame, and you end up with this equation. So it all comes down to finding the derivative of cos theta prime with respect to cos theta, right? Because that's the only quantity which is being transformed. And that you can do from this equation here, right? So I've just left it here so you can pause it and see the steps. But the basic idea is, you get that Jacobian by just a simple chain rule differentiation, and then you put it all together, and then you get, again, the Doppler factor keeps appearing, right? And so we're gonna, give it a name, call it delta, the relativistic Doppler factor, and you get d omega is d omega primes times delta square, right? And now it's good to have a little bit of intuition about what this Doppler factor is. So let's say that you're having a look at this Doppler factor, and let's say you're in an ultra relativistic regime. So gamma is extremely high, right? Beta is almost close to 1, which means that this Doppler factor is going to be extremely high unless theta is very close to 0, right? So if theta is very close to 0, then this d omega basically is the Doppler factor kind of goes to 0, and d omega is going to go to 0 as beta approaches 1. So what does it mean? It basically means that in an ultra relativistic situation, even though d omega prime, which is kind of the extent of solid angles, might be very large. So let's say isotropic emission. So you have a large extent in solid angles. In the lab frame, you're going to see a very small extent of solid angles because of that, this Jacobian, which is going between these two frames, and that Jacobian is basically the Doppler factor. So I would encourage you to, do some numerical calculations to get a sense for what this looks like. You can write a simple program to actually plot this Doppler factor. So you get a little bit of intuition, and it's good to have that intuition. Okay, so last thing I want to talk about is actually putting all of this together, right? All the things we just spoke about, and calculate the radiation pattern of an accelerating charge. Okay, so I'm not interested in the total power anymore, right? It's not just d energy by d time. I just want to also know the angular distribution. So I need to have energy in the numerator, time, but also beam solid angle, right? So I'm going to put all of these transformations together and then figure out how this quantity transforms. Now we know from last week that that's the equation for the amount of power radiated per unit solid angle and this theta here is the angle made with the acceleration vector. Okay, so just mind that, because I've used theta for two different things here. So I've used theta before this week to mean angle made with the relative velocity vector when we did aberration of light. But I just want to keep the same notation in this equation here as last week, so you kind of recognize the formula. And there, theta was the angle made with the acceleration vector, right? So just keep that in mind, which theta is meant. Okay, so how do you transform this quantity? So let's see how to transform energy. Okay, so energy is the zeroth component of a 4 vector, and we're talking about electromagnetic radiation. So the other 3 components are the photon momentum. So you put that together, you know how the Lorentz transform works. Energy in frame K is going to be gamma times energy in frame K prime plus beta times. You basically have the momentum, but the X component of it, right? So if you have an angle theta prime, which is made by the radiation, then the total momentum times cos theta prime is the X component of the momentum, right? So you put all of that together, you get this transformation for energy, right? This is just simple Lorentz transform taking the 4 vector for radiation, right? The 4 momentum for radiation, sorry. And of course, the 4 momentum, you use the fact that photon momentum is just given by energy divided by the speed of light. And it has a direction, of course. So that direction depends on the direction in which the photons are moving. And, I'm just taking the projection onto the x-axis here, okay? So x being the axis of relative velocity between the two frames, right? So if the relative velocity between the two frames is along the x-axis, radiation is moving along an angle theta prime, then cos theta prime gives you the projection onto the axis of the relative velocity. anyhow, so you get, you get the same Doppler factor here. Again, I don't want to be in the primed frame, so I want all the angles to be in the unprimed frame. And so I get, energy is equal to the energy in K prime frame divided by the Doppler factor. Okay. Now we just did time dilation, right? We just spoke about the time dilation plus the canonical Doppler shift. So I know how dt transforms now. So dt is just going to be dt prime times the Doppler factor. Okay. Now what am I left with? Just the solid angle, which I just derived. So solid angle is going to transform like that. We just derived that, right? So you put all of that together, you get that the power radiated per unit solid angle goes, you have to multiply it by Doppler factor to the power -4, and then you go from the primed frame to the unprimed frame or the laboratory frame. So let's put all of that together, right? So this is Doppler factor times to the power -4 times the equation we had for the power radiated per unit solid angle from last week, right? Again, here, just remember that this theta here, I'm soon going to replace that with a capital theta. So just remember that here, this theta has to be capital theta. I'm just going to soon, replace it. But I kept this theta here so you kind of recognize the formula. But it's not the same theta as that goes in the Doppler factor. Okay, so the theta going in the Doppler factor is the angle made by the radiation. Okay, so the line of what we used to call line of sight, just the direction of radiation, the angle made by the direction of radiation with respect to the vector v, which is the relative velocity between the two frames. That's the theta that goes into the Doppler factor. This theta is the angle made by the direction of the radiation with the acceleration vector. Okay, so let's specify what the acceleration vector looks like. For the general case, it becomes very complicated, the algebra. So I'm just going to take two easy cases. So I'm just going to say, let's say acceleration is parallel to velocity. So now those two thetas are the same, right? Because acceleration and velocity are parallel. Those two thetas exactly, have the same definition. And we just had the transform, we know how to transform acceleration from the rest frame of the particle to the lab frame. And we know how to transform sine theta because we have a sine square theta here. So again, from the aberration formula, we know how to transform sine theta. You just put all of that together. And again, you can pause this video to go through the algebra like I've done here. You get this expression, right? So that's the lab frame measurement of the power you're going to receive from an accelerating charge if the acceleration is parallel to its velocity, right? Now, let's see what happens if the charge is ultra-relativistic. The key factor here is this, right? I mean, this factor basically blows up if beta becomes equal to 1 and theta becomes equal to 0, because this factor goes to 0 and 0 to the power -6 is going to blow up, right? So let's Taylor expand this around cos theta equal to 0 and beta equal to 1, because that's where it's going to blow up. So I'm going to Taylor expand beta as 1 minus 1 over 2 gamma square. Again, you can check this. This is just a Taylor expansion around beta equal to 1. And the Taylor expansion of theta to quadratic order is this. So you know that. You put all of that together, get rid of fourth order terms. You get, you get this as a Taylor expansion around theta equal to 0. And you put it in the equation, you get something that looks like this. Again, you can pause the video and go through the algebra here. About what's really happening graphically is, let's say you have a charge which is moving along the x prime axis, right? And it's being accelerated along its velocity, right? Acceleration parallel to velocity, that's the case. I mean, the rest frame of the charge, it's just going to give out dipole radiation, right? And this is the radiation which we dealt with all of last week. That radiation has a sine square theta dependence, right? So when theta is 0 along the x-axis, there's no radiation. And then, this is just a cut in the frame of the paper. And, the analogy I gave was the child with the flotation device, right? So this is actually going to look like the flotation device in 3D with the child along the x-axis, right? Now, if you see the same thing in the lab frame, there's going to be a huge amount of aberration, right? And this equation gives you what happens close to theta equal to 0. By the way, if theta is, very far from 0, right, then this equation already kind of tells you that if theta is very far from 0, then this whole value is going to be pretty small, right? So you can also see it in the Taylor expansion here. As I increase theta, the denominator is going as 12th power of theta here, right? So which means that this value goes to an extremely small value. So if you're very far from, the axis along which the charge is being radiated, then you basically get zero radiation, right? So if you just look perpendicular here, you're going to get zero radiation. But if theta is exactly 0, then again you get 0 because the numerator has theta square. So exactly along the axis, there's no radiation either. But again, there's at very small values of theta. Again, in the denominator, you have theta to the power 12. In the numerator, you have theta power 2. So at very small values of theta is where all of that energy is going to go, right? It's going to go at the small values of theta. Again, this is a section in the plane of the paper. You need to kind of rotate it about the x-axis it's kind of going to look like a cone, right? It's going to look like a very narrow cone. And that angle there is roughly 1 over gamma, right? So most of the radiation lives in this pattern in the lab frame. Okay. Now let's do case 2, which is a little more complicated because of the geometry. Now we have perpendicular acceleration, and so we need to now figure out the angle between the acceleration and the direction of radiation, right? So now we have 3 vectors to worry about. So you have the relative velocity vector v here, you have the direction in which the radiation leaves. Okay, so let's say I'm just going to, without loss of generality, going to choose it in the plane of the paper here. But now you have an acceleration that's perpendicular to v, but it need not be in the plane of the paper, right? It can actually be pointing right at me, coming out of the paper, or going into the paper, or at any azimuth angle, right? So let's say that angle is phi, right? So if I take the acceleration cos of phi, I get the projection in the plane of the paper of the acceleration, right? So that's cos of phi projects the acceleration into the plane of the paper. Now, if I want the angle between the acceleration and the direction of radiation, then I need to multiply that by sine of phi, right? So cos of phi projects the acceleration in the plane of the paper times sine of phi projects it in the direction of the radiation, right? So cos of the angle, now I'm going to call it capital phi, because that's the angle which goes into the Larmor's formula for dipole radiation. That's the angle between the acceleration and the direction of emission. So I'm going to call it capital phi with this, I'm going to use this symbol for capital phi. Now again, everything is in the primed coordinates because we are doing everything in the frame of the particle. That cos is just going to be equal to the dot product between 2 unit vectors, right? 1 unit vector along the direction of radiation and 1 unit vector along the acceleration direction. Now, how do you get the dot product? Well, you see how to project the vector, right? So you can first project the vector onto the plane, and then in that plane, project the vector onto the direction of emission. So cos of capital phi prime is theta prime, sorry. I'm going to call this capital theta prime. Is going to be equal to cos of phi times sine of theta prime. Okay, cos of phi prime times sine of theta prime. Okay, so we can easily get sine square of phi prime. It's 1 minus sine square of capital theta prime is going to be 1 minus cos square of capital theta prime. We need sine square because that's what goes into Larmor's formula. And yeah, so you basically have cos of the value and you're trying to find the sine square of the value. That's easy. Again, you put all of these things together. I'm not going to go into the algebra. You can pause it and work through it yourself. Again, you get this expression. Okay. Now again, if gamma is far greater than 1, I'm going to do the same expansion to try to see what the radiation pattern looks like. And in this case, you're going to end up with a situation where if you put theta equal to 0, the radiation doesn't go to 0. Okay, so it looks slightly different. Okay, so let's see how it looks like. That's the rest frame of the particle. Now the acceleration is perpendicular to the velocity, which is along the x-axis. And so you get the same kind of kind of this donut kind of shape, but turned 90 degrees, right? Because the acceleration is now perpendicular to the velocity. Now let's see what happens to the radiation pattern. So if you have some large value of theta, again, theta to the power 12 in the denominator, that's going to overcome everything for large values of theta. So you don't get any radiation at large values of theta, right? But if you have theta very close to 0, you can actually put theta equal to 0 and the numerator doesn't go to 0, like in the previous case. So actually most of the radiation leaves close to theta equal to 0, and the angular extent of radiation, again, is because of this gamma square theta square combination here. This extent of the beam is going to be 1 over gamma, right? So that's going to be the radiation pattern. Again, everything confined into a very narrow set of angles for an ultra relativistic charge. And so this is basically called relativistic beaming. It's just comes from the fact that because of all the Lorentz transformation between frames, even though the particle might have kind of a very broad radiation like a dipole or even isotropic radiation in its own rest frame, to an observer, the radiation looks very highly beamed in the direction in which the particle is moving. Okay, so that's called relativistic beaming. And yeah, so I'm going to stop here. Again, I want to stress that I don't expect you to basically remember all of these things or perfectly derive them in a crunch time kind of setting. But I went through all of this just to give you the expressions which we will be using later, but also give you the intuition for how you would apply the concepts of aberration, how you would apply the concepts of 4 vectors transforming, the relativistic Doppler factor. So yeah, it's just an example of, let's say I gave you a quantity like this, how would you transform it, right? I mean, you might encounter in life some other quantity, right? And this is just an example of how you would go about transforming between the frames.